Assalamu alaikum dear students. Today we shall discuss one of the most important theorem of calculus, that is Rolle's theorem. So the statement for this theorem is: let f from closed interval a b to R be a function with the property first is f is continuous on this closed interval a b, that is everywhere on this interval this f is continuous. F is differentiable on this open interval AB, and third property with which f have, that f of A equals to f of B. Then according to Rolle's theorem, there exists a point C belongs to open interval AB such that f dash of C equals to 0. That is, if we have a function from closed interval to R which is continuous on closed interval, which is differentiable on open interval of this closed interval, and at end points the value of the function is same, then there exists at least one point say C belongs to this open interval or between the two endpoints of this interval such that at that point the derivative of the function is 0. What is geometrical interpretation of this? Now consider a function whose graph is as shown in this fig, and interval a b such that a is less than b. Now here this function is continuous, which implies that there is no jump or break in this graph of this function. So clearly it is continuous. It is differentiable within this interval. This means that endpoints it is not differentiable, because at endpoints function is never differentiable. But if we consider the points within this interval, at each and every point this function is differentiable, because there does not exist any peak or any vertex, hence it is differentiable. Also f of A equals to f of b. Here f of A is the point on y-axis, whereas f of b is the point in on y-axis, which implies that when we consider this f of A equals to f of b, which implies that both these two points, that is f of A as well as f of b, should lie on the same line which is parallel to x-axis. This means that f of A equals to f of b. Now clearly at C there is a point this on this graph. When we draw a tangent at this point x equals to C, this tangent is parallel to x-axis. When tangent is parallel to x-axis, which implies that the slope of this tangent equals to the slope of x-axis, because you studied in this class 11th that the necessary and sufficient condition for two lines to be parallel is that their slopes must be equal or identical. Now here we have a tangent to this, and we have x-axis which are parallel, which implies that the slope of this tangent equals to slope of this x-axis. Also slope of x-axis is 0, which implies that the slope of this tangent is 0. Hence slope of tangent as x-axis is 0. Now geometrically this f dash of C gives us the slope of the tangent at this point, which implies that f dash of C equals to 0, because f dash of C gives us the slope of the tangent at point C. Here slope of tangent at C is 0, which implies that f dash of C is 0. So this is the statement and geometrical proof of this Rolle's theorem. What about the converse? Is it true or not true? The converse of this theorem is not true. That is, if f dash of C is 0, where C is the point within this interval, it does not mean that this function is differentiable on this open interval AB. It does not imply, as in general, that the function is continuous on closed interval AB. It does not imply in general that f of A equals to f of B. So this condition that f is continuous, f is differentiable, f of A equals to f of B is only the sufficient condition. Sufficient condition means that if when function satisfies these three properties, it implies that this f dash of C equals to 0. But it is not necessary condition. Necessary condition means that when f dash of c equals to 0, it should imply that these three properties. But in general, it does not imply that this function, that the given function whose f dash of c is 0 satisfies the given three properties. So simply Rolle's theorem is only the sufficient condition for function such that there exists a point where the derivative is 0. So let me consider example. Here we cannot apply the Rolle's theorem to those functions which do not satisfy the three properties. That if function is not differentiable on this open interval, then we cannot apply this Rolle's theorem. Now if it is not continuous, then again we cannot apply. That is, to non-continuous function, Rolle's theorem is not applicable. Similarly, if f of a equals to f of b, we cannot apply the Rolle's theorem. Hence, if the function does not satisfy either of these three conditions, then we cannot apply the Rolle's theorem. What about the converse? Now I will show you the converse by an example. If we consider the function f of x equals to 0 when 0 less or equals to x less or equals to 1, this means that in this interval, closed interval 0 to 1, this function is 0 and is 1 plus x when x greater than 1 less or equals to 2. Clearly f is not continuous at x equals to 1, because at x equals to 1 the value of the function is 0, while as its right limit is 2, which implies that it is discontinuous at x equals to 1. Hence we can simply say that it is discontinuous. It is not continuous in interval 0 to 2, closed interval 0 to 2. Also f of 0 is not equals to f of 2, because f of 0 is 0, f of 2 is 3, which implies that f of 0 not equals to f of 2. When function is not continuous, which implies that it is not differentiable, because when function is continuous, it does not imply that the function is differentiable, but when function is differentiable, it always implies that this function is continuous. Hence this is not a differentiable at x equals to 1. So this means that this function does not satisfy the three conditions of this Rolle's theorem. Now if we consider the function in this interval 0 to 1, open interval 0 to 1, which is subset of this given interval, that is 0 to 2, and if we consider any point on this, everywhere the function is constant, that is 0. When it is 0, this means that its derivative is 0, which implies that f dash of x equals to 0 for all x which belongs to interval 0 to 2, 0 to 1. In particular, if we consider any t, fixed t, then f dash of t equals to 0, where t belongs to this open interval 0 to. Hence there exists a point where derivative is 0, but function does not satisfy these three properties of this Rolle's theorem. So this means that it is only sufficient condition but not necessary condition. Verify the Rolle's theorem for f of x equals to x square plus 2x minus 8, x belongs to minus 4, 2. Firstly, we have to check whether it satisfies the first three properties of this Rolle's theorem, or three conditions of Rolle's theorem. Here f is continuous for all x belongs to minus 4, 2, because f is polynomial. You know that polynomials are continuous functions, and f is differentiable also in open interval minus 4, 2, because polynomials are differentiable functions. Now we will find f of minus 4, that is 0, by substituting the value of minus 4 in the given equation, and f of 2 is 0 by substituting the value of 2 in the given function, which implies that f of 4 equals to f of 2. So it satisfies the three conditions of Rolle's theorem. Hence, by the statement of Rolle's theorem, there exists a point c belongs to minus 4, 2, such that f dash of c equals to 0, because Rolle's theorem is applicable. Here f of x is x square plus 2x minus 8, which implies that f dash of x equals to 2x plus 2 by differentiating. Hence f dash of c equals to 2c plus 2. but f dash of c equals to 0, which implies that 2c plus 2 equals to 0 or c equals to minus 1, which implies that this c equals to minus 1. Here minus 1 belongs to minus 4 2, which implies that Rolle's theorem is applicable because there exists a point c belongs to open interval minus 4 2 such that f dash of c equals to 0. So for this function Rolle's theorem is applicable and we find such c. Is Rolle's theorem applicable to the given function, that is f of x equals to greatest integer function? What about its converse? Since you know that the greatest integer function is not continuous at the integral values, that is when x equals to 1 2 3 minus 1 minus 2 minus 3 so on, the function is not continuous, which implies that here 5 6 7 8 9 are the integrals or the integers which belongs to the given domain, which implies that f is not continuous at these points. Hence in particular f is not continuous in interval 5 9. When it is not continuous implies that it is not differentiable at these points, which implies that f is not differentiable in 5 9. Similarly f of 5 is greatest integer of 5 is 5 because 5 is integer, and f of 9 is greatest integer of 9 which is 9 because 9 is integer, which implies that f of 5 not equals to f of 9. So this means that this function does not satisfy the three conditions of Rolle's theorem. Hence the function is this, we cannot apply the Rolle's theorem to this function. Now what about converse? Now here this interval 5 9 contains an open interval 6 7. Here this open interval 6 7 does not contain any integer, which implies that everywhere on this f of x is constant. You know it, which implies that when f is constant, which implies that f dash of x equals to 0 for all x which belongs to this subset of this given interval, that is open interval 6 7. Hence in particular, if we consider a point c belongs to 6 7, then f dash of c equals to 0. But this 6 7 open interval is the subset of closed interval 5 9, which implies that there exists a point c in open interval 5 9 such that f dash of c equals to 0. So this means that f dash of c equals to 0 is, there exists a c such that f dash of c equals to 0, but the given function does not satisfy the three conditions of Rolle's theorem. Hence converse is not true in this function. So this means that this f dash of c equals to 0 does not imply us that the function satisfies the three conditions of Rolle's theorem. So inshallah in tomorrow's video lecture we shall discuss the mean value theorem. So thank you.